Hey everybody, Miss Mokano here. We're picking up where we left off last time. So this is going to be 1D Kinematics Part 2. And today we're going to be talking about different ways to represent motion. This is really important. There are definitely a lot of questions about this on the AP test. And we just need to become really familiar with these. They may seem a little bit daunting at first, but if you learn a couple of tricks about how to interpret these different ways of representing motion, it will become second nature soon. So let's get right into it. So one way that, let me present actually, one way that we can see very often is this motion diagram. Okay, and I'm sorry about this bar at the bottom. I can't get rid of it, but I think we can see well enough regardless. So basically, these black dots represent where the object is at every given second or a given interval of time. But the important thing is to realize that what we're seeing here is equal intervals of time. So for example, this black dot object, whatever that is, could be a car or anything, it's moving, let's say in 1 second is moving from here to here. And then the next second is moving a little bit further, so the velocity is higher. And then it's moving a little bit further yet again. So we can see that on this diagram, we have a way to show the position of the object. The time is shown just by the black dot themselves. And then we have the velocity. We get an idea of the velocity by how far apart the dots are spaced in equal intervals of time. And then, of course, if the velocity, the green arrows, if they are changing, we know that the object has to be accelerating. If it's whether they're going up or down, there is an acceleration. All right, another way to represent motion that we'll see is, with a set of axes like this. We have a y-axis over here, and there would be an x-axis down here, and it's showing this rocket moving in the y direction. And we see a vector showing acceleration in the positive y direction. And we see here coordinates showing y, f. A lot of times, just learning the symbols is really helpful. So x and y usually specify position. So here we're specifying y, the position in the y direction. F, the subscript f would mean f, final position. I would be initial position. So we're saying that this rocket started here. This is the initial position at time ti, which is the initial position, and it started with velocity v subscript y. That is the velocity in this direction, in the y direction, at the initial position. Same thing up here. So we end up at position y subscript f because it's the final position. This is where we end up. We end up with a velocity of v in the direction y, subscript y, and another subscript f because this is the final position. And then we end up tf. This is the time at the final position. And yet another way of representing motion would also be this velocity versus time graph. And we'll be talking a lot more about these. All right, so here's another representation of motion. So we have at rest, constant speed, speeding up or slowing down. These are the different states of motion. So at rest, obviously nothing's happening. Constant speed, like we see this guy on a skateboard, he's moving at constant speed, equal amounts of distance in equal amount of time in the same direction. Speeding up, so she is running here and she is, how can we tell she's speeding up? We have these snapshots taken of her. Let's say they're a second apart. So here she ran this far in the first second, and a second later she's a little bit further, and then yet another second later she's even further. So she's speeding up. And then slowing down, we have, let me see if I can get rid of that bar. We have that car, the red car. So you can see that in the first second, it went further than in the second, and then in the third second, it went even less far. So it's slowing down. So just the visual representation of motion. So again, we went through this before. One thing I want to say is that when we're solving problems, this is crucial. Making some kind of diagram that represents the motion is very, very important. And also putting right on the diagram all the known and unknown quantities. In problems, we'll be given a few known quantities depending on the problem, and we will be asked to find other quantities which are unknown. So if we make a diagram like this, it's going to be very helpful in solving the problem. So here are more graphical ways of representing motion. So we have x versus t, or position versus time graphs, and we have velocity versus time graphs. And these, we're going to be working a lot with these kind of graphs, and we're going to be looking at basically what their shape tells us. What does it mean that they have a certain slope? What does it mean that the slope is increasing or decreasing? What does it mean that the values are positive or negative? All these things are very important, and they tell us something about the motion of an object. All right, so all of these ways to represent how objects move. And let's start now, get a little bit more into these kind of graphic representations. So we're going to be talking about position, time, and velocity versus time graphs. All right, so here's position versus time. Very simple motion. Nothing's happening. The object is at rest. So if we look at this graph, we can see that the object at time 0 over here is at a certain position. And as the time goes on, we're moving along this way. As time goes on, the position stays constant at whatever it was at the beginning. So the object is not moving. Nothing's happening. The slope is 0, meaning that the velocity of the object is 0. Obviously, if it's not moving, it has no velocity. So here's the velocity versus time graph for the object we just described before. So we said it was not moving, so the velocity is 0 the entire time that we're recording that object. So something a little bit more advanced in that kind of motion is constant speed. So here we have a motion diagram. So let's kind of decipher how we would read this in a problem. So we're showing our object here, this little red cart. And as we talked before, we're given equal time intervals. Okay, so before we're seeing those black dots, right now we're seeing this red cart. It doesn't really matter. The important thing is that you have some kind of representation of the object, that it is done at equal time intervals. Oh, I'm sorry, I'm pointing at, so here's the time, 0 seconds, 1 second, 2 seconds. So every second, we are shown where this little cart is, where the object is. And down here, we're told the position of the object. So at 0 time, so at the initial position would be 0 meters. Then 1 second later, it's at 10 meters. 2 seconds later, it's at 20 meters. And basically, this is translated into this position versus time graph. So the really important thing is that all these graphs that we're going to be talking about, all these ways of representing motion, they are equivalent. You could deduce one from the other, and they should all tell us the same story. It's just that we may want to look at one rather than another, depending on what we want to know about the story, but they should basically be equivalent. All right, so here, this position versus time, we have the same story, but in different formats. So position 0, right here, we're at 0 time and 0 position. At 1 second, we're at 10 meters. At 2 seconds, we're at 20 meters, just like we saw here, and so on. And we can see that the slope of this position time graph is constant, meaning that it is going at constant speed. And as you see here, it's going 10 meters every second. So that's constant speed. One other thing, so not only is the is the speed constant here, because we're told that by the slope of the graph. But the other really important thing that we need to realize is the slope positive or negative? And that will tell us in which direction the object is moving. So if we have a positive slope, as in this case, then we know our object has a constant velocity in the positive direction. That's what the meaning is of positive slope. So you can even tell from this diagram, the object obviously is moving in the positive direction. It's increasing. The position is increasing as we move along. And if we had a negative slope, if we had a negative slope, then it would have meant that the object was also moving at constant speed, but it was moving in the opposite direction, in the negative direction. So now, kind of taking the same exact situation here, but making it onto velocity versus time graph. So as we said here, we said we had a constant velocity in the positive direction. So here it is on the velocity time graph. We got a constant velocity, 10 meters per second, and it's a positive value. So they're all equivalent. This graph right here is equivalent with this graph and with this motion diagram. All right, so let's now go to yet another kind of graph that we're going to be seeing, which is acceleration versus time. So remember what we said about acceleration. Acceleration is change in, by definition, acceleration is change in velocity over change in time. So in this situation where we have constant velocity, the change in velocity over this time is 0 because the velocity is not changing. It's constant. So that's what this graph shows. The acceleration then will be 0 over that time period. All right, so let's do something a little trickier now, which is speeding up. Let's see what that object looks like. So here we are, 0 second, 1 second, 2 seconds, 3 seconds. Okay, so here's the time. Here's where the object is at all of those time intervals. Now here we could see in 1 second this object traveled this far from 0 to 2. Second, it traveled from 2 to 8, so a larger distance. In the next second, it traveled from 8 to 18, so even a larger distance. So we know the object must be speeding up. And how are we going to show this on a position versus time diagram? Well, remember that what we said before, that on a position time diagram, really the slope of that position time curve is what gives us the velocity. So how we show that the object is speeding up is that that slope is increasing. So if you look at this curve, the slope at any given point as we go in this direction is always increasing, meaning our velocity is increasing. And again, everything, the slope at all over this curve is positive. So that means our velocity is in the positive direction, which we can tell by looking at this diagram. The object is moving from smaller x values to larger x values. It's going into the positive direction. So in a position graph for an object that is speeding up, the slope will be increasing each second. We just said that for this graph. And the slope is positively increasing if moving in the positive direction, as in this graph. But let's say the object was moving in the negative direction. Then we can see from this graph, the slope is still increasing as we go along this way. The slope is increasing, but it is a negative slope. So that means our object is speeding up still because the slope is always increasing, but it is going in the negative direction. All right, so I am about to run out of time, so I'm going to leave this here and we will continue next time. And thank you guys very much. We'll see you soon.